files, things, and if you just run those commands, you can pull it out of my home directory.
What's the name of the file?
Oh, it's in the home dir, so it's tilde greg arei /mgv.tar.gz. So if you copy that to somewhere you want to work and then you extract it with tarx vzf mgv.
Linux side or Solaris?
Linux. Has anybody been able to grab it yet? Haven't really tested it out. All right, I'll fix that real quick. You did? Okay. So then, let's see. Oh, it's because you're doing it to /practice. So if you do it, if you make that directory or something.
Yeah, I did.
Okay, so don't put a slash in front then.
How do I X?
No, just go over and, oops.
There you go.
Yeah. So go into that practice folder for you, and then run that tarx vzf command. Have you extracted it?
Mm-hmm. Sure.
Okay. Oh no, so you've already got it, so are you in?
Well, I'm in practice now, but I don't know where.
Okay, so go ahead and run ls real quick. It just has problems.
Yeah. And so there it is, but for some reason it won't let me.
Okay, well here, let's just do this then. So let's go into here. Okay, cool. Yep, and there you go.
Thanks.
Yeah, so this has some sample make files and stuff that we'll be using. All right, what class are you all in? Are you in 202 or 201?
Yeah.
You also?
201, yeah.
Okay.
162.
Yeah, so you've been told you have to use make files this term?
Yeah.
Yeah, they are useful. So I'm now I guess a senior in CS, but my specialty is Linux desktop applications. So I have a lot of experience with make and then debuggers and et cetera. And that's what this will be about. So the things we'll be talking about are make, GDB, and Valgrind. Do you know what make is? Have you used it before for anything?
No,
Okay. The whole idea is that it's to automate things, so that somebody wants to build your program, you don't have to go ahead and you don't have to give them a list of commands like I just gave you to try and copy the source code over or to compile your program. That's obviously a pain. It's hard to get correct, and there's always little details you miss. So make is a sort of universal way to run a set of commands that you give out with your program. GDB is a debugger. And I don't know if you've noticed yet when you're programming, but your ability to more or less use the tools that help you program, like a debugger, compiler, editor, are really what are going to restrict how well and how quickly and how easily you can program. So debugger is probably one of the most important tools that will help you in creating software.
I just got a quick question. What's the difference between having like a make file or like a shell script?
There is not much. The difference is that make is pretty. There are some abstractions that make has that allows it to be more portable. Mm-hmm. I'll get into that a little bit, but it's basically the idea is if not all shell scripts operate the same way. There's different shells. There's different environment variables that people have, and make has things there that allow people to run your make commands on multiple shells, and it will still work. Not to mention multiple operating systems. And Valgrind is another debugger and profiler. But it's more aimed at memory management and allowing you to find out everything that's happening in memory with your program. So I already told you a little bit what make is, but the idea is you automate a set of tasks. Compiling is the most common set of tasks that you're going to automate. But it also you can automate testing, which is a very common use. People run make test, and you'll go ahead and run through a whole bunch of test scripts that work on applications. You can automate anything else too, like you have to mail in your program to your professor, you can automate that using make. So maybe make send, it will send it to your professor. So let's go ahead and look at the first make file. It's in the folder make prog1/make file. And you're going to open that up in some kind of editor, whatever you're comfortable with. Yep. So makefile is, whenever you call make, it looks at a makefile. And it's just any file in the current directory with the name makefile, starting with a capital M, is the makefile. Its structure, on a very simple level, is it's just rules and recipes. So a rule is your unindented lines. You typically have a rule and then a colon. That's sort of a set of commands that you're going to be giving to make. And hello world is the name of this first one, which all it does is compile hello world. Under that, you've got your recipes, which are the commands you're going to be giving to your shell. So right under that, you should have your g++ hello world.cpp, which you should be able to tell compiles hello world.cpp. Whenever make is invoked, it always calls the first rule. So if you go and exit out of your editor right now, and you run make, you'll see it just runs g++ hello world. It runs the recipe right under that first rule. And so you can make your recipes do anything. If you have a command for, like I said, emailing your professor, your assignment, you could go ahead and put that under hello world, and it would perform that task whenever you call make. You can also call rules explicitly. If you go ahead and run make space hello world, it'll still do the same thing. It'll call the hello world rule. You can try that out if you want. The other big thing to take from it is that the indentation in that file is tabs, which is very important. If you're indenting with anything other than tabs, make will complain and not work. And it's a very cryptic error, so just make sure you indent with tabs and make.
And it doesn't matter what the tab is set to, it just...
It's a tab character.
Okay.
So you don't. So some editors will expand that to spaces, but if you do that in a make file, it won't work. Lots of editors like Vim, I know, will automatically make sure it doesn't do that in a make file. So like I said, you can call rules explicitly. So let's go ahead and look at the second program 2. And go ahead and have a look at that make file. It should look mostly the same, except there's 2 rules. There's another rule called clean. So if you go ahead and run make and build hello world again, it should create a binary called hello world. All right. If you go in ls and check out your directory, you'll see your binary. What's pretty common in almost all projects is they also, along with the make command, which builds the project, they also include a make clean, which removes everything that's not needed to build the application. So basically, it leaves only source files behind. If you run make clean, you'll see what it does right now. Make space clean.
It always echoes everything out to the...
Yep, yeah. And you can actually change how it echoes, but that's a little bit advanced.
Okay.
Yeah, so you can call rules explicitly like that. Yeah, if you make space and you give it a rule, it'll call whatever rule you want explicitly. It'll just start with that recipe as opposed to starting with the first one. So if you want to make another common one is someone makes a test rule, and then they put a bunch of test cases under it, so then you run make test. It'll test their application. So a little bit more advanced, if you go into the program 3, is you can have prerequisites, which creates a sort of dependency tree of rules. So let's go ahead and look at that. Rules can be files as well as, and dependencies or prerequisites is what it says on the slide, can also be files. The idea being, if you have a prerequisite that is a file, it will look if that file exists, and then it will assume that that the prerequisite is satisfied. So the way this is going to work, if you just run make, it's going to run the first rule, and when it looks at the first rule, it'll see that it has a set of prerequisites in order to complete that first rule. It should say like hello world.o, I believe, right? Yeah. So what that means, it'll go to the hello world rule, and before it can run the hello world rule, that means it has to satisfy the hello world.o prerequisite. In order to satisfy that, there's a hello world.o rule, so it'll go and run that, and so on until it sees hello world.cpp as a prerequisite for that hello world.o rule. Hello world.cpp exists, so that prerequisite was satisfied, so it'll go ahead and run the hello world.o rule, compile that, and then go back up to the hello world and create the binary. So if you run make now, you'll see how it runs those two things in sequence. Yeah, do you sort of understand the dependency graph is what it's, yeah, you can think of it as like as a binary tree, or not binary, but a tree or a directed graph that goes down of dependencies.
So it actually runs this before it runs the...
Yeah, so what it does is it goes to hello world, and then it says, okay, I need to satisfy that, I'll go satisfy that, and then it keeps going. Yeah, so then, but make clean is not a dependency of anything, right? So if you run make, it's not going to run make clean. You have to explicitly call make clean if you want to remove that. And this is a pretty common way of people building their projects. They split it up where it compiles all the .o files separately. And the reason for that is when you run, if you modify your CPP file and you run make again, it's going to say, okay, I've already created that binary. I don't need to rebuild. And it's not going to recompile. You have to run make clean and then run make again. If you compile it this way, where you actually create .o files individually, it'll say my .o file is out of date. It'll rebuild just that one file, and it'll work.
So if I do make here and then we make again, it won't...
Nope, go ahead and try it.
Okay.
Yep, it says that file is up to date. So actually, if you've got a large project with many source files, and you run make, and you only modify one file, it's really nice to do it this way, because it'll only recompile that one file. That's all it really needs to, as opposed to if you had your one G++ and listed a whole lot of CPP files in there, it would have to recompile the whole project. Okay. Yeah, all right, so let's go ahead and look at program 4, which has variables. Just like in, do you have a question?
We'll just go back, and so when you do the G++, the lower dot, or when you do the one below a dot C, that just creates the object file? Is that
Yeah,
correct?
if you do a -c, that's exactly what it does. It takes in a source file, creates a .o file,
Okay.
which is, it's sort of in between a complete binary and
Yeah.
in between the source file. It is a compiled binary, but it only represents that one file. It hasn't been what's called linked.
Linked with the rest of them, yeah. Okay.
Mhm.
And so by default, if you call G++, it's giving you, it's doing the full compile.
Yeah, G++ actually looks at it's one of the few programs in Linux that looks at the extension of the file name. It looks at the .o or .cpp and interprets there what to do with it. It's like the golden rule on Linux is never to do that, but G++ does it.
Okay.
And so if you give it a .o, it'll say, this is an object file, I'm going to compile it like an object file.
Okay.
If you give it a CPP, it'll go ahead and do the whole thing.
Okay. And so you can specify it so it creates the object.
Yeah, -c means stop before, don't do the link, that means just create object file.
Thank you.
Yep. So in program 4, there's some variables, and this is another pretty common practice, which is if you see there's a variable named out file defined, and it may seem a little bit silly here. It's like, okay, it's only used 2 places, but really what it's there, the reason people like this and use this commonly is 3 months down the road when some other guy wants to modify your build system and just change the name of your binary because they changed the project name or something, you don't have to hunt things down. And so the syntax is pretty simple. You just variable equals value, and then to use it, you have this $, open parentheses, variable, close parentheses. And it'll substitute that set of characters for the value of that variable. It's pretty straightforward. And so all this does is it's the same code, except if you modify that out file line up top, it'll go ahead and modify what the name of the binary that's created is. It's just a neat little trick.
Okay, and then so the first one usually, the first rule is a default rule, so that doesn't necessarily get taken as a rule because there's no colon after it?
Oh, no, that actually, the out file isn't considered a rule. Anything that you list off outside of a rule, just straight down, that will be run always.
Okay.
Yep.
And then so it defines the first rule with whatever it said with the colon after, is that correct?
Yeah, so it's going to go ahead and run hello world as the first rule. If you run make, it'll just do that. You won't see the out file equals value,
Okay.
but it will substitute for it.
Okay.
Okay. And sort of wrapping up make is, it's actually used all over the place. Pretty much every single application that you use on Linux right here uses make. It's also used on OS X. It's used all over the place. It's fairly universal. Although people actually use programs around make. They don't just use a straight up make file because it's not as dynamic as people need it to be. So there's a whole set of tools around it, autoconf and CMake, that people used so it'll detect your system, say, okay, I have these things, am I able to install, and maybe give the user a nice message saying you need to install this to use this program, etc. Do you have any questions about make?
No.
Okay, so yeah, when you're using, or when you have to do this in your class, it's fairly straightforward, and you go ahead and look at the source code here. Make files are fairly universal in how they're designed. So the next topic is GDB, which is the GNU debugger, and it's probably the most useful tool for programming on any type of Unix system. It's actually used all over the place because it's a very, very well-made debugger. It's used on Windows quite a bit as well. So the idea is you create a program, you run it, it crashes, or it's not doing what you think it should do. How do you figure out what the problem is? And looking through your code to try and find the problem isn't very practical. It's not, you might be able to do it in a tens of lines program, but imagine trying to do that in a real project that has tens of thousands of lines. You would never find the bug. So what GDB does, it sort of locks your program in an environment where it saves the state of the program whenever it crashes, as well as lets you pause it and control how it executes. Maybe say only run the next command or the next line of the program, which is amazingly helpful. The only caveat is when you compile your program, you need to use -G along with your G++ or your GCC, which adds debug symbols into the program. It makes the binary a little bit larger, but it's really no harm to you. So let's go ahead into GDB prog1 and check out and compile it. And compile that folder. You'll see it creates an executable called segfault, which, imagine what it does.
I'm sorry.
So it's in MGV, which is that folder that it creates /GDB/program prog1/segfault. Actually, the binary is not there. You have to go into that folder and run make. It'll compile it. Okay, so do you all both have the binary? Okay, so the way to run, let's see what this next slide is. Yeah, the way to run something in GDB is you do GDB space the name of the binary, and that will run the binary inside of GDB. So go ahead and do that. It's GDB space segfault in this case. And it brings up a GDB prompt, which is sort of like a whole new shell that is specific to GDB. So then if you type run, it'll start the program, or run and then enter. Okay, and it should give you something about how there was a seg fault. And it will even tell you exactly what line and print out that line for you. So if you've ever had a seg fault before, if you had that information, it's amazingly useful. If you want to go ahead and look at the code too, type L, or list is the full command. GDB has it's like Vim, where you can do everything a million ways, and there's always a shorter way. So R will run, L will list, and that shows you the surrounding lines, and you can see, I'm obviously dereferencing a null pointer here. So you were told exactly where your seg fault occurred. It's pretty amazing. So Control D or exit will log you out of that shell and bring you back to bash. We can go ahead and then check out, yeah. And then we can go ahead and check out, actually, go ahead and rerun that program real quick. So GDB space, the name of the program. Okay, and then do run, make it seg fault again. And then once you see that, you can, that has told you what line number it's on, but typically it's a little bit more complex than that. Typically there are multiple levels of issues that are going on. So imagine you call a function, you pass it in a null pointer, and then inside that function it dereferences it. You're going to be seg faulting inside a function, but the problem wasn't actually inside that function. The problem was outside when you passed in the null pointer. But you should have been checking anyways, but just imagine that situation. So run backtrace. And backtrace is typically, the process of someone debugging is, they run the program with GDB, they see a seg fault, they run backtrace immediately without even thinking about it because that's just what you're always going to want to do. And backtrace sort of prints out the function call stack that has happened. So right here, there were no function calls. There should only be a number 0, right? And let me make sure. Yeah, there's only one line there. It says number 0, and it says in main because you're in the main function, and it tells you what line number it occurred. So this sort of gives you a frame of reference for what's going on. Now, if you want to print that variable, say you only had that one line number, or maybe you didn't know that the previous line was a null pointer, you can go ahead and print that variable and say, okay, what's wrong here? Why is this seg faulting? So if you print foo, you see, okay, that variable that I'm dereferencing is 0. Now I know what's going on. You don't have to analyze the whole program source to see what the value was there. And you can do that with any variable. You could even print foo. You can't write all of C, but you can write the typical things that you would see where you're dereferencing variables. So if you did print star foo, it would just say, okay, that would be a seg fault. So go ahead and Control D. Let's log out of here. Now, when you go ahead and run that same program, go ahead and run that same program from the command prompt at seg fault. It should just say that it's seg faulted. Yeah, it just tells you segmentation fault, which is not very helpful. And typically that's what you're going to run into when you're working on your application. You're going to be working on some code, you make some modifications, you run your program, it says seg fault, and you go, okay, now I get to load it back into GDB and repeat whatever I was just doing. That's a pain. So what you can do then is use core dumps. Core dumps are disabled on these computers by default because they can take up a lot of space if you run a program like Firefox and it crashes because of a segmentation fault. It's going to dump all the memory of Firefox into a file, and that will use up all your quota space. For your programs, it's very helpful. So go ahead and run this ulimit-c unlimited line. Okay, and then go ahead and rerun the program.
Just make again? Or?
Just /seg fault. Yep, and now it says seg fault core dumped. If you look in your folder here, you do an ls, you'll see a file named core, and that's a binary dump of the state of that program. GDB can then go ahead and use this and tell you what the state of the program was when it seg faulted. So the idea again is you're working on your program, it seg faults, and you had to type all this input. Now you don't have to go and rerun your program. You can just go ahead and feed this core dump into GDB and see exactly what happened. So to do that, run GDB space the name of the program, which is seg fault, space core, or the name of the core dump file. Yep. And that'll go ahead and bring you into GDB and give you all sorts of, and give you that same line that you saw before. So you can do everything you were doing previously. You can print foo, you can run L and see the code around it, and you don't have to go ahead and rerun it in GDB.
So can you also do this if you don't do the -G option? Or no?
You can. What you will get though is you won't get that line of code. It'll say, maybe if you're, it'll give you some binary data. It'll say it happened at this memory address into the program. And you're in 201 now, so have you been introduced to some assembly?
A little.
Yeah,
A little bit.
you'll be able to see the assembly code is the short answer. And that's not always that helpful. If you're really good at assembly, maybe you can reverse engineer on the fly or something, but otherwise, that's all you get. What -G does actually puts the source code, it puts tags saying this group of assembly is this line of source code. So it gives you a lot nicer output. Yep. So frames are the other thing I was talking about, where you run backtrace and you get a 0. So go ahead and program 2 and run make in there. And then go ahead and run it. Watch it segfault and core dump. Cool. Now load that core dump up in GDB. And you'll see there's 2 lines now. So go ahead and run L. Curious what it'll say there. Oh, I load it up in GDB first. Okay, so now hit L. Click.
It's list.
Yeah, that L or list are the same thing. Yeah, and it's not happy. So if you run backtrace, you'll see why. And the reason is that number 0, which is the current frame, is mem copy. And that's basically the information you would get if you didn't have -G. Because mem copy was not compiled with -G, is the problem there. Yeah. So what's actually happening if you push up and you go to that frame, it'll go up 1 frame to number 1, or not the arrow. Type the word up. Yeah, I should have been more clear. Yeah. So now that changes your frame to that number 1, which was actually inside of your segfault.cpp file. Now that's code that you've created and you've compiled it with -G. So now if you type L, it'll show you the source code. And so what's happening is I'm trying to copy a string, goodbye cool world, into a null pointer. So what it's going to call that strcopy function, it's going to give it a null pointer and a string, and that's going to cause a segfault inside of that function. So that frame 0 was inside of that strcopy function, which is what the problem was. You don't have the source code for the strcopy function, so it couldn't give you any nice information. So you want to move up a frame to where your source code actually is. A more explicit way is you can type frame space and give it a number. It'll move you to that frame. So if you're like 5 or 6 frames deep, you just frame space 0 or whatever is relevant, and it'll move you there. Yeah, I think that's about.
Just to reiterate, it goes from that, when you say up, it goes from the pound 0 to pound 1.
Yep.
Is that correct? Okay.
Yeah, so if you type frame 0, it'll move you back to frame 0. And then you're back in that binary source file that you can't really use for anything.
Okay. So based off of what we see up here, we'll know where it's at, because this says mem copy and this one's segfault.
Yeah, so basically what I do, at least when I'm debugging it, you run backtrace and you look for what files have a .cpp or a .c file that is relevant to you. So typically the library you're calling isn't going to have the error in it. It's typically your source code using that library incorrectly. And so you'll look for an error in that, or basically the lowest depth at which your source code exists. Okay, so the next, what is this? Breakpoints. Oh yeah. Okay, so breakpoints are the other big feature of GDB. So if you run, or if you type the command break space segfault.cpp:8, just into GDB. It'll say breakpoint set number 1 set, and what that means, next time your program runs, it'll run until it reaches line 8, which is what the :8 is, and then it'll pause and let you do whatever you like. Oh, it says breakpoint at hello world CPP line 5, but that's from an old slide. So now if you go ahead and do run again, you'll see it'll runs up until it hits that breakpoint. And if you type L, you'll see what line that was. Oh, did you do the breakpoint? Yeah, there you go. So it says it runs and it says breakpoint 1 hit, and it tells you what line that was on the str copy line, which means it's going to pause right before it calls that function. So it hasn't seg faulted yet. If you type next means go ahead and try and run this line, and then don't go inside the function. Don't try to debug that. It'll seg fault because it just tried to go to that null, dereference that null pointer. Alternatively, you could have run step, which means go into the function and debug any code inside of there. So next and step are the two ways to control it. The other way is continue, which just says, okay, ignore it, go ahead and resume doing whatever you want to do. In theory, all this will cause a seg fault because step can't actually debug the binary str copy function. Any questions? Okay, so that's GDB. There's a whole lot more to GDB, and feel free to explore it, but it's way beyond the scope of introductory CS. It's a huge program.
You create scripts for like...
I believe there is a way to have like an RC type script, like something that's run initially when you run GDB. I don't know how to do it.
Or remember that you want to put breakpoints in certain places.
Yeah, so a lot of programs, how do people do that in Linux land? A lot of IDEs, like if you use Visual Studio, they have the same type of thing. You know, you click on a line, it'll send that command to the debugger to debug it at that line. I think there's a way to do this in Vim. But typically the way it works is your editor is what ties that in. So you're going to say this line of my source code is where I need to debug. The idea being like if you add in lines above it, you want that line to change, among other things. So you're going to have to explore that. I'm sure someone has made a Vim plugin for that, though. Yeah. Valgrind is the other big guy. And what Valgrind is the other tool. Your program crashes, it's not doing what you expect it. You GDB it. If it's not obvious, you Valgrind it. If it's not obvious, then, well, you're going to have a hard time. So what Valgrind does is it analyzes all of your memory. It's a simple way to put it. It sort of watches how your program interacts with memory. It sees if it's forgetting that it allocated memory. It's also seeing if it's accessing memory that's not initialized, which is a very useful tool. So let's go ahead and look at the first program. It's an mgv/valgrind/prog1. So yeah, if you run make, it'll create the memleak program, which, well, do you all know what a memory leak is?
Yep.
Okay. So what a memory leak is it's your program can allocate memory, like if you use new in C++ or malloc in C. If you don't delete it or you don't free it, it's considered a memory leak. And over time, you can consume all of the memory on your system, or you could just, well, that's the big issue, and if you have ever run an old version of Firefox or an old versions of lots of programs, and eventually your system just starts going very slowly or the program crashes, that's likely the cause. So to check for a memory, this program has a memory leak, as the name says. So if you run this valgrind space memory leak space this hyphen leak check equals full, it'll run your program and then it'll analyze its memory. Oh, sorry, it's /memleak. Sorry, you have to actually give it the command you're going to run. Yeah. Did it work then? Mm-hmm. Yeah. Yeah, so it gives you a whole bunch of information, but the big line to be worried about, yeah. Oh yeah, I guess you have to do this -- leak check equals full before the executable. So go ahead and push up and then try and move that in front. Because at the bottom there it says definitely lost 59 bytes in one block. So it's saying it lost it, but if you run it with this memleak -- leak check equals full and then the executable, it'll tell you where that memory was allocated, which is a very useful bit of information. Yeah, right there. So it says at memleak.cpp on line 3. So if you go ahead and look at the source code, open it up in whatever editor you like, you'll see what's happening. I'm just basically allocating memory and not freeing it.
Are we able to view?
Just in whatever editor of your choice.
Okay, so this memory.
Yeah, memleak.cpp. Yeah, so you'll see I just am creating a new character array and returning. So Valgrind's not happy with that, as it shouldn't be, because I'm never freeing that memory. Here, it's a pretty silly case. Your program's going to exit. You're going to get that memory back. It's not a big thing, but if it's inside of a loop, or if who knows what else you might be doing, if it's a server application, eventually you're going to have some issues. Not to mention, your professors should probably be checking for memory leaks, because it is a very bad practice. That was a very simple example, and it's not always the most practical for small applications. Another area where Valgrind is incredibly useful, though, is for program 2. And it's this issue called uninitialized jumps. So go ahead and run Valgrind on it again. So it's Valgrind space -- leak check equals full space / unijump. Yeah, you can just run it like that. You'll be fine, actually. Yeah. And so it should print out something. We'll get it. Yeah, there should be a line there about uninitialized jump. Yeah, conditional jump or more depends on uninitialized values. What that means is you've got an if statement or a while or some type of conditional, is what those are called, where the condition is dependent upon an uninitialized variable. So go ahead and look at the source code in some editor. And you see I make an integer, and then I say if that integer is true, then do this. If it's false, do this. That integer is never set anywhere, so you don't know what's going to happen there. That is an incredibly common bug in programs. Not to mention if it's a while loop and you're whiling on something that you haven't set. So if your program is just acting weird, you don't know why, run it in Valgrind. It'll tell you're not initializing this value in a conditional. It's an amazingly helpful tool.
Do these debuggers come with Ubuntu installed,
Nope.
or do you have to?
Yeah, you have to install them. So it's just apt-get install Valgrind. I'm not sure, but I can add it. We're obviously videotaping it now, so we're trying to make it more friendly for people remotely.
Okay.
Yeah, I'll make sure to add it.
Yeah, that'd be awesome. This is really helpful.
Yeah, good. Any other questions? That's basically all I've got. Yeah.
In this condition that you said, this is a common error. I mean, I forget, but if the if evaluates 0 as being.
Yeah, so you don't know what CNT, it's CNT, right? That it's a variable. Oh, no, it's called cond. So if you don't initialize it, it's garbage, right? It can be anything. It can be
Anything.
It can be 0 or some non-zero number.
Yeah.
Obviously, the probability is that it's going to be a non-zero number, but you don't know. Not to mention, it works if you've got, say, a while loop. You're trying to increment a counter. Maybe that counter you thought was 0 initially, and it's never going to happen. So, regardless, if you're iffing on something that's not set, you're doing something that you shouldn't be doing. Is really, or you forgot about something. So. Anything else? No? Well, thanks for coming.
Thank you.